Hello everyone, Irfan Amin here, and today we are going to study basic discrete structures. So basically this course is based upon computer science 201. It is needed in both computer science and both computer engineering. So in this video you are going to watch the basic discrete structures and what is discrete math introductions and sets. So let's start with our first. So what is discrete math? Discrete math is the study of the discrete structures used to represent discrete objects. For example, many discrete structures are built using sets, and you must have known sets as a collection of objects. Here it is written. So there are various examples of discrete structures built with the help of sets, and that is combinations, relations, and graphs. So what is set? A set is an unordered collection of objects. These objects are sometimes called elements or members of the set. For example, vowels in the English alphabet. Vowels equals to, and these are the third brackets, I don't know, curly brackets, A, I, O, U, and another one. First seven prime numbers, x equals to 2, 3, 5, 7, 11, 13, 17. So these are a collection of data or objects. So they are called sets. They are written inside the curly brackets. Representing a set. A set is represented by listing the numbers of set. It is also called enumerating, and definition by property using set builder notation. For example, x such that x has property of p. Let us see an example. Even integers between 50 and 63. So we can write like this, listing the members of set. E equals to 50, 52, 54, 56, 58, 60, and 62. Then in number 2, definitions by property, we can write like x such that x is greater than or equals to 50 or less than 63. So they say even integers between 50 and 63, so we can write like this. And in the instruction we can give that x is in given integer. It is also called x has a property of b. So we have to write the property. Is it integer, or it can be anything, a real number or a rational number, anything. So if enumeration of the member of set is heard, we often use ellipses. Example, a set of integers between 1 and 100. So you don't have to write most of the numbers. So what you can do, like, there are 100 numbers between 1 and 100. So you can write 1 to 3, then some dots, 3 dots, comma, and 100. You don't have to write whole 1, 2, 3, 4, 5, 6 up to 100. So important set in a discrete math. We must remember these notations. Natural numbers, it is called n, and we can write in 0, 1, 2, 3, blah blah blah. After 0, they are called natural numbers. And integers can be any numbers, but they don't have any decimals or anything like fractions. Like they are denoted as z. It can be minus, it can be 0, or it can be beyond. So less than 0, 0, and after 0 it can be anything. And positive integers, z plus, we have to denote by like that. So positive integers are after 0. So 1, 2, 3, you cannot write 0. 0 is not, there is a confusion, I don't know. I will make another video on that. Okay, so positive integers are 1, 2, 3 to anything, not any minus or something, because they say it is positive integers. And rational numbers are any numbers that can have any fractions, and real numbers are any numbers, real numbers. Okay, so equality of set. So definitions is the two sets are equal if and only they have the same element. For example, 1 to 3 and 3 to 1, they're pretty basically the same thing, right? So you can write 1 2 1 2 1 3 2. You have to note that the duplicates don't contribute anything to a new set. Remember that. So remove them. The order of the elements in a set doesn't contribute anything new. For example, are 1, 2, 3, and 4 and 1, 2, 2, 4 are equal? Absolutely no. Universal set. Special sets. The universal set is denoted by U. Yes, everybody knows that because we used in our previous studies. If you are familiar with sets, universal set are all of the objects under the consideration, and the empty set is always denoted as phi or a curly bracket. So either you can write just phi or just write any curly brackets. And Venn diagram, a set can be visualized using Venn diagrams, and we can write V equals to AB. So there is a set, we can write, it's a Venn diagram, it's universal set, there are some dots, and A, B, C are inside a diagram, so we can say V equals to A, B, and C. And now what is a subset? For example, a set A is said to be a subset of B if only every element of A is also an element of B. I repeat, every element of A is also an element of B. So we use A is subset or equals to B to indicate that A is subset of B. So see, inside B there is A, so we can say A is subset of B. If it was like that, B was inside and A was outside, so it will be B is subset of A, and we can write this define this subset A is a subset of B like this. For all, this sign means for all x is element of A is x of element is in x is element in B. Empty set or subset property. So there is this is the theorem. You can check it, like you can check while I can skip. So there is a theorem. This is the proof. You can note down, you can pause this video and you can note down. Okay, now let me jump to another thing. So this is the another theory, and always remember that phi or any null set is always a subset of any set, because you cannot write 0. Remember that one. Subset property. So this is also theorem that S is a subset of itself. Like anything is a any diagram is a subset of itself. For example, A is subset of itself. If there is a B, B is subset of itself. So this is a proof. It is a very simple one. Basically it's same thing. We used our previous formula for all x is an element A, a subset of x is an element of B. So just replace A and B with S, you will get the answer, and there's the end of the proof. You might need it, so you can also note down this. And a proper subset, now we will see there. A set is said to be proper subset of B if only A is subset of B and A is not equals to B. We denote that A is a proper subset of B with the notation A is subset of B. So is this a proper subset of B? Guess it. I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay, yes, of course it's a subset. A is a subset of B. So what is cardinality? So this is the another interesting thing. Let S be a set if there are exactly n distinct elements in S, where n is a non-negative number. We say S is a finite set, and that n is the cardinality of S. The cardinality of S is denoted by mod X. So basically it denotes the number of elements in a set. For example, V equals to 1, 2, 3, 4, 5. If you see mod V, so the number of elements in this set is 5. So very simple. For example, in a range of 1 to 20 numbers, what is the cardinality? It's 20, because 1, 2, 3, if you count them, there are 20 numbers. And what is the cardinality of phi? It's always 0, because there is nothing. The number of elements in this phi is 0. Infinite set, this is a simple definition. A set is infinite if it is not finite. For example, it it doesn't have any range, or it doesn't give any limitations from which you will go. So we can there's an example: the set of natural numbers is an infinite set. For example, n 1 2 3 dot 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 ellipses. So it means it continues. So this is an infinite set. The set of real numbers, for example, it is an infinite set. And now power set. Given a set S, the power set of S is set of all subsets. The power set is denoted by P and S. So let's see an example. What is the power set of phi? Or phi phi equals to phi. What is the cardinality of P phi? The cardinality is always 1. So assume there are some numbers 1 2 3. Probability of 1 to 3 equals to, it will be like this: phi 1 2 3 1 2 1 3 2 3 and 1 2 3. So what is the cardinality of this set? It is absolutely 8. Let's count: 1 2 3 4 5 6 7 8. So if set is cardinality S equals to n, then what will be the power set cardinality of the power set? Let's think for 5 seconds, and you can check this, you can sort out this, and you can mention in the comments below what was your answer. Just comment page 17 answer, your answer. You can comment in the box below. I will give you the credit. Okay, but now the n-tuple, it's also called tuple. Sets are used to represent unordered collections. So ordered and tuples are used to represent an ordered collection. So you can guess that if something is ordered collection, you can say that is an ordered. If it is unordered, then it is an unordered. Unordered collection is called n-tuple. Definition: an ordered n-tuple x1 to x2n is an ordered collection that has x1 as its first element, x2 as its second element, and xn as its ninth element. So n is always greater than or equals to 2. So coordinates of a point in the 2D plane is, let's assume it's 2 to 16. So just you can get the definition, and if you do some exercises you can sort out this problem. And Cartesian product. So let S and T be sets. The Cartesian product of S and T, denoted by S into T, is a set of all ordered pairs St, where S is element of S and T is element of T. Hence, as if you multiply S into T from our previous equations, as if for X, S and T, where S is an element of S, intersects or into T is an element of capital T. So if you see the example, you will understand. There are two sets: S equals to 1, S equals to 1 2, and T equals to ABC. So if you multiply S and T, you can see 1A 1 into A, 1 into B, 1 into C. Again 2 into A, 2 into B, 2 into C. Note that if you multiply it in reverse, T into, like we did now, S into T, now T into S, you can see that A1 A into 1, A into 2, B1, B2, B, C1, C, and C2. So note that S into T is not equals to T into S. Remember this, don't think that the product is always the same. It's different. It's not like that 2 2s are 4, 2 4s are 2 4s are 8, and 4 2s are 8. They're same. But don't think in this term that S into T and T into S are completely different. So cardinality of a Cartesian product is same. Just find the number of, first find the Cartesian product, then find the number of Cartesian product, like this. It is very confusing. It's not confusing, actually it's a long process. For example, John Jane, first multiply A into B as the instruction: John Jane, John and John Laura, dot dot dot, and finally Mike Laura. So the number of elements are here are A into B are 9. And you can see in other word that there are 3 elements in A and 3 elements in B. So multiply them, you will get the same answer. So a subset of a Cartesian product A into B is called a relation. from a set A to set B. Just remember that this is the definition of cardinality of a Cartesian product. Set operation definition: let A and B are sets, and the union B A and B are denoted by A union B is a set of blah blah blah. So this is the general definition. You can read it from there. So we can denote it like that. And remember this sign, this is a union sign, or the A union B for X, where X is element of A, union X is element of B. So we are union means the elements in A and B together. For example, let A be 1 2 3 1 2 3 6 and B 2 4 6 9. So we can write 1 2 3 4 6 9. We don't have to repeat the numbers where they, because the 2 is in A, it is also in B. So we if it is union, we can write it once. So this is very simple. We studied in not primary, actually secondary school or high school. It is very clear. So just for revision I'm saying. So intersection is same, but it's a common one where they cut. For example, there are no 1 2 1 2 3, there are 2 4 6 9. So they both have one in common, and that is 2. So A intersect equals to 2. So this is the definition. You can read it from here, and there's nothing to explain like that. It's the same, just the sign, this sign changed to this sign, nothing else. So next, move on to the next slide. Disjoints are like mutual exclusive. You can also say it's a mutual exclusive in discrete math. While you are studying discrete math, sometimes you have to say it as a disjoint. It's actually disjoint. There's this mistake. Two sets are called disjoint if their intersection is empty. So we can say that if A intersect B, or any set intersect another set is in phi, means nothing, that don't intersect. We can say it's a disjoint set. So for example, A goes to 1 2 3 6 and B goes to 4 7, and are this disjoint? Yes, because there is no intersection point. So if they don't intersect, we can say that it's a disjoint set, or the two sets are mutually exclusive. So set difference is also simple. That, for example, let A and B are sets, the difference of A and B denoted by A and B. So we can write like that. This explains that elements that are in there's means there will be A alphabets A, but not in B. So A minus B means elements that are in A minus B means that are not in B. The difference of A in B is also called the complement of B with due respect A. So alternatively we can write A minus B for X is element of A intersects X is not element of B. So see from here, 1 2 3 4 5 7 1 5 6 8. So we have to cancel B from here. So for B we can cancel 2. We can cancel we can cancel what they have count. We can cancel 5, we can cancel 1, we can cancel any other thing. No. So we can write 2. We have left 2 3 and 7 because we cancelled 5 and 1 from A because they are in B. Complement of a set is also simple. We can go through it. Let U be the universal set, the set of all objects under the consideration. Definition: a complement of the set A denoted by A is the complement of a set A with respect to A. So it means that complement means without A, elements, everything without A. For example, there is a universal set 1 to 8 and A is 1 2 3 4 5 8, and A complement is every numbers except A. See, 1 3 5 is not included because 1 3 5 is always included in the set. So as this is a complement, except this we can write other numbers. So this is 2, for example, 2 4 6 7 8.